All right, hello and welcome again to one of Mr. Martin's math videos. This is a video for BC Pre-Calculus 12, Chapter 5.4, looking at equations and graphs of trigonometric functions. All right, so it is oftentimes the job of mathematicians to model the behavior of a particular phenomenon with some kind of function that relates one changing variable to another dependent variable. So we talked about how trig functions can be used to model cyclical kind of phenomena that we see around us. So now we're going to really be applying it more specifically to those phenomena. So for situations where an object is oscillating or repeating some kind of cycle or motion, trigonometry is used to model such behaviors. In this section, we'll be looking at several models attempting to do this very thing, as well as how to solve them. All right. So first, we're going to look at how to solve trigonometric equations graphically and also algebraically. We're just actually going to be more verifying our answers graphically, but we will want to approach this algebraically first. And so we do have a domain, which also gives us the units that we're going to be working in here. We're going to be in degree mode and not radian mode, since we're dealing from a domain of 0 degrees to 360 degrees. And we want to solve this equation here. All right, so I'm going to rewrite this equation to get started here. I have 12 cos 2x minus 45 degrees plus 8 is equal to 10. Okay, and just like in any algebraic expression, our goal, our approach here is always to isolate the variable, in this case, the x variable right here. So we need to move everything else over to the right-hand side of the equation. All right, so I'm just going to start doing that. The order at which you move things to the other side of the equal sign is the opposite of your BEDMAS order of operations. And so for BEDMAS, you start with brackets, exponents, division, multiplication, addition, subtraction. For algebra, you want to do the opposite. You start with addition, subtraction, then multiplication, division, and then exponents and brackets, those kinds of things. And so I'm going to start by subtracting 8 on both sides, okay? And in the same step, I'll divide both sides by 12, okay? Just kind of combine those two steps. So that's might be a little bit confusing, actually, now that I see it written out, but hopefully you can follow along here. So these 8s cancel out. The 12s cancel out. It's going to give me cos bracket 2 bracket x minus 45 degrees is equal to 10 minus 8 is 2, and then 2 divided by 12 would give you 2 over 12, or reduced to 1 over 6. Okay. The next algebraic step I want to do is I want to move the cosine here function over to the other side algebraically. So just like you learned in grade 10 trigonometry with SOHCAHTOA, when you're trying to solve for the angle, you need to use the arc of the trig function. And so here, algebraically, essentially you're doing arc cos on both sides. So essentially that cancels out, so you end up with 2x minus 45 degrees is equal to arc cos of 1 over 6. Okay. So at this stage, we're going to then use our calculator here to solve, this side of the equation here for our arc cos. And so when I first need to make sure my calculator is in degree mode, which it is, I put arc cos 1 divided by 6, and I end up with 80.4. Okay, I end up with 2x minus 45. Now here, if it was a value that finds itself like on your unit circle, you want to be using exact values then in those situations. But for us, 1 over 6 is not any of the x coordinates on our unit circle, so we just use our calculator to solve for that. That gives me 80.4 degrees. However, that's not the only thing that it gives me. That's not the only value that it gives me here. If you guys remember, so 80.4 finds itself to be, about here, right? And so here I get 1 over 6 was the x value, and I get some kind of y value, okay? However, if you guys remember the cast rule, right, tells us which quadrants do we have a positive ratio for cos, okay? And so we know that the first quadrant, all trig functions, all trig ratios are positive, but for cos you also have quadrant 4 gives you a positive x, this would be 1 over 6 here, right? So cos, arc cos of 1 over 6 gives you this angle, all right? But it also gives you this angle, all right? So we need to make sure we include both. The first angle, that first line here, that's the 80.4 that we got, okay? But we have to, remember the second angle. The second angle then would be 360 minus 80.4, right? Because you're going to get matching reference angles here, right, away from the x-axis. So you know that it's going to be 80.4 less than 360 degrees, okay, for our other answer. So if I have 360 degrees minus 80.4 degrees, I'm going to end up with my other value, which is going to be 279.6 degrees. We can always double check. Minus 80.4, and sure enough, 279.6 degrees is the other thing that cos, arc cos of 1 over 6 is equal to. So I have to kind of split my equation into two parts. One using the 80.4 answer, the other one using the 279.6 degree answer. Okay, and then from here I continue my algebraic work. All right, so here again, now that the cos is gone, I divide both sides by 2. All right, and then this gives me x minus 45 degrees is equal to 40.2 degrees, and then I add 45 degrees to both, and I end up with a solution of 85.2 degrees. That's one of what x is equal to. The other one is from this equation. So again, divide both sides by 2, and then I get x minus 45 degrees is equal to 139.8 degrees, and then plus 45 degrees plus 45 degrees. I end up with x is equal to 184.8 degrees. All right. So I've got two solutions here for x. Okay, I have this one here, this one here. Both of them fit within my domain. Okay. Now there's one last variable we have to consider here. Okay, if you guys remember our format here for these kinds of equations, the 12 would give us an amplitude, our amplitude of 12. The 45 degrees is our phase shift. The plus 8 would give us our, our d value, which moves the equation up or down by a certain amount. And then our 2, this 2 here gives us our b value, which allows us to figure out what is our period for this equation. Okay? Because if the period, a typical period for a cosine function is 360 degrees. And so if this just had a period of 360 degrees, the two values here 85.2 and 184.8 would be our only two solutions. But because here I have a b value of 2, that's going to change the period of this cos wave, and I might end up with more, depending on the period I end up with the b value, I might end up with more solutions, okay? So if you guys remember the equation for period, you take the 360 degrees divided by the b value, okay? Specifically the absolute of the b value. So in this case, it would be, let me continue to the side here more. So this case would be 360 degrees divided by 2, which would give me a period of 180 degrees. So this means that this function repeats every 180 degrees. So it's going to go through 2 full cycles in this domain here. So that means I probably need to keep looking for more solutions. I'm going to have more than 2 solutions, okay? So, for example, here, an additional solution from this point here would be the value that I got, 85.2 degrees, and you can add or subtract your period at this stage. So subtracting my period wouldn't make sense here, just because I'd end up with a degree value that's less than 0 and outside of my domain. So I'm going to add 180 degrees. I can add 180 degrees here and still fall within my domain here. Okay, so that's going to give me my next value of x, which is going to equal, what is this? 265.2 degrees. Okay, so that's another solution here. So I have this solution, I have this solution, and over here, if I add 180 to 184.8, that's going to give me a solution that's greater than 360 outside of my domain. However, I can subtract 180 into here and fall within my domain. So I'm going to do that. That leaves me with 4.8. Let me write this out properly, which is going to give me my other x value, which is going to give me 4.8 degrees. Okay, so you have this solution and you have this solution. So 4 solutions in total comes out of this, okay? And we'll see why that makes sense. Let's now verify our solution by graphing to see if we can make sense of this. So to graph this, I'm going to take this equation as y1 and the 10 as y2, so I can see where the line crosses the 10 line. So I already have 10 in here. I just need to change this. 12, let's just start over here. 12 cos 2 bracket x minus 45 bracket plus 8. My y2 is equal to 10. I graph. Whoa, okay, let's zoom, affect our zoom here, change our zoom. 300 is there, 350, 60 is about there. Okay, so, and here I can check your solutions just by finding the intersect of the 2 lines. And so the one intersect here, that's my y-intercept. Let's see if I might have to zoom in here to get that one. Okay, so this intersect is 4.8, essentially, which is one of the solutions that I got. Okay, the line goes up, crosses the 10 line at 4.8 degrees. When it comes back down, crosses at 85.2 degrees, which is the solution I got. And then it crosses again at 184.8, which is the solution we got. And one last time within our domain at 265.2 degrees, which is our 4th solution. Now, of course, it keeps intersecting the line, the yellow line here. However, we only have to find solutions within that domain. However, in future questions, we're going to have to solve for the general solution, if you guys remember that term from some of our previous notes. Okay, so we've confirmed that these 4 solutions are the solution for this equation. Okay, let's try another problem together here. Again, we're going to be solving this algebraically and graphically, and then we're also going to be stating a general solution and not just a solution within this domain. We'll start with this domain, but then we'll come up with a general solution. Now this domain tells me that I need to be in radian mode, not degree mode. So I'm going to go ahead and in my calculator change things to radian mode right away, just so I don't forget to later. All right, put that to the side. Here I have my equation, which is sine bracket pi over 4 x minus 6 bracket bracket equals 0.5. My next step from here, because there's no d value or amplitude value or a value, right, is that I can, arc sine both sides of my equation essentially. So I end up with pi over 4 x minus times x minus 6 is equal to arc sine is 0.5. Okay, now arc sine 0.5, or sine theta equaling 1/2, is on our unit circle. All right, so my y value is equal to 1/2 in two places on my unit circle. It's equal to 1/2 at this location here. And it's equal to 1/2 over here as well. Okay, so at pi over 6, I know that unit circle is painful on the eyes, but pi over 6 and 5 pi over 6 are the two places that sine theta is equal to 1/2, which is equal to the y value on the unit circle. So that's where my equation is going to go off, okay, in those two different directions. All right, so for pi over 4, x minus 6 is equal to, I said, pi over 6, or 30 degrees, but we're working in radian here, pi over 6 radian. And the other equation would be pi over 4 x minus 6 is equal to 5 pi over 6. All right, and then I go to work algebraically. I'm going to divide both sides by pi over 4 divided by pi over 4. And that leaves me with x minus 6 is equal to, you multiply by the reciprocal, reduce your fraction, you end up with 2 over 3 here, okay? And then plus 6, and I end up with x is equal to 6 2/3, or if you turn it into an improper fraction, it gives you 20 over 3. Okay, now you want to check if that fits within your domain. Okay, 20 over 3, or 6 2 over 3 is 6.66, where 2 pi is approximately 6.28, right? So we want to, this value does not fit in our domain, okay? This is too big, all right? What about this solution here? So we'll come back, but for now, this initial algebraic solution does not fit within our domain, but it will be helpful for us in finding a general solution, all right? For this one, math steps similar. Divide both sides by pi over 4, which gives me x minus 6 is equal to, again, you multiply by the reciprocal, and then you reduce, which gives you 10 over 3, then plus 6, which leaves me with x, and then it'll be 6, 10 over 3, but 6 would represent 18 over 3, plus 10 over 3 gives you 28 over 3, which is equal to about 9.3 repeating, which is also outside of the domain, also too big. Okay, so neither of our solutions that we found algebraically fit within our domain that we have. Okay, does that just mean that there's no solution within that domain for this equation? No, the answer is no. There is a solution within this domain, but again, just like last time when we only had 2 answers algebraically, but there were actually 4 answers, we have to figure out what the period of this wave is. Okay, and again, our period equation is equal to, in this case, instead of 360, it's 2 pi over b. And 2 pi over, in this case, b is equal to pi over 4. And then you divide those, and you end up with a period of 8. Okay? So in this situation, the period is larger than the domain. However, we might be able to get some answers here, okay, despite of that. So let's try to reduce this first solution that doesn't fit in our domain by one period to see if that one fits in our domain. Okay, that solution fits within our domain. So if I have 20 over 3 minus 8 and put as a fraction with a denominator of 3 would be 24 over 3. Okay, that gives me a negative number, so that gives me negative 4 over 3. That one is too small, okay, to be in our domain, so that doesn't work. So for this side of the equation here, there are no solutions that fit within my domain. Okay, we'll try the same thing here. 28 over 3 minus 24 over 3. Here we get a solution that works, negative 4 over 3. Okay, so x is equal, oh sorry, not negative, positive 4 over 3. X is equal to positive 4 over 3, or 1 and 1.3 repeating, and that is a solution that fits in our domain as stated above. So this would be the only solution for this graph in this domain. Okay. However, that doesn't mean that's the only solution. Okay. But let's confirm this first by graphing, and then we'll look at the general formula. So again, graphing, this is my y1, this is my y2. My calculator is already in radian mode, sine, and then I'm gonna pi divided by 4, and then x minus 6, bracket, bracket, and then this is going to be 0.5. Graph, whoa, lots of lines here happening. So again, my domain, if you guys remember, is about 6.28 based on 2 pi, right? And so this solution here, 6.66, is too large. It's outside of my domain. The only other solution then is this point here, 1.33, which is equal to 4 over 3. Okay, so that confirms the solution there. All right. Now, when it comes to a general solution, because based on the graph, this does go on forever and ever and ever. So to find the general solution, then I just need to start with both of my starting fractions. I can do 20 over 3 or negative 4 over 3 or 28 over 3 or 4 over 3. It doesn't matter too much here, but I can say x is equal to, let's say, 20 over 3 plus the period multiplied by n, which is an integer. Okay, so, and then the same thing starting from the other solution of 28 over 3 plus 8n. However, this is assuming, both of these equations assuming that n is an integer. Okay, so if you multiply integers, positive and negative numbers, to 8, and then you add that to the two solutions you got algebraically when solving for this this trig equation, that'll give you all the possible solutions for an infinite domain. Okay, so that would be your answer in general form. All right. So let's see if you guys can give this a try here. Your turn, A and B. Okay, for A, you're just solving within that interval. You can confirm by graphing, but I want you guys to solve algebraically. And for the second one, you're determining the general solution. Okay, so go ahead and pause the video. and give those a try, and then come back and let me zoom out here, come back, and we'll go over it together. All right, hopefully that went well, and you were able to find all the solutions for each question. Let's go over it together now. Again, my domain is in degrees, and so that I have to, I'm going to put that into my calculator right away, just so that I forget about it later. Then you just start algebraically trying to isolate that x variable. -7, -7, and then I'll do this first couple steps all in one here. That's going to give me cos x minus 45 degrees is equal to 10 minus 7 is 3, divided by 4 is 3/4. All right. And then x minus 45 degrees is going to be equal to arc cos, right? Because we're doing arc cos essentially on both sides. Again, we're isolated the x variable. That's just what we're doing here. The trig ratio, the cos ratio 3/4 doesn't exist on the unit circle, so I'm going to use my calculator to tell me what the values of those are. So, where it's not a special point on the unit circle. It does exist on the unit circle, but it's not a special defined point on the unit circle, as defined by our unit circle formula sheet. Anyways, there gives me my first solution. So x minus 45 degrees is equal to 41.4 degrees. Okay. Now remember, again, just like the first question that we looked at, we're using the cast rule. If that exists in quadrant 1, and because cos is positive, it will also exist in quadrant 4. Okay, and we'll have the same reference angle. So if I do 360 minus 41.4, I'm going to get my other value, or my other degree that cos or arc cos 3/4 is equal to, which in this case 360 degrees minus 41.4 degrees is equal to 318.6 degrees. So x minus 45 is equal to 318.6 degrees. And then finish off your algebra. Plus 45 plus 45 plus 45s everywhere. Here I end up with x is equal to 86.4 degrees, which fits within my domain. Okay. And then for this one here, I get x is equal to 363.6 degrees, which does not fit into my domain. Okay, this one's too big. Okay, does not fit into my domain. So this is for sure one of my solutions within my domain. The other one is not. It's too big. Okay. However, again, we have to take into account the period of this wave function, and because the b value is 1, the period of this function would equal 360 degrees. Okay, divided by b, and if b is 1, then you just get 360 degrees, right? So that's our period. So if we apply the period to this one, we get something that's greater than our domain. So we would get a number that's in the 400s. Yeah, so that wouldn't make sense for us. However, for this one here, if I do 363.6 degrees minus the period of this function, I end up with a solution for x within my domain at 3.6 degrees. And that is my other solution. Okay, so you have to use that period. Okay, we can confirm this using a graph once again. My equation should already, my graph and calculator is already in degree mode. For cos bracket x minus 45 close bracket plus 7, y2 is equal to 10. Let me just double check my equation. Ooh, I need to bracket. I don't know why I have so many brackets here. Delete. and then plus 7. Okay, let's clean that up a little bit. Graph. And then here's my wave function. Okay, 360 degrees is about there. Note that this 363.5 or 0.6 falls outside of my domain, so it's not a solution. This is the one I got algebraically, the 86.4. Then, it's not gonna. I have to zoom in to isolate this one. Then I get the 3.6 degrees right close to the y-intercept there as another solution. So both of those are solutions. You may have forgotten about that second one, but that's why we do these practice problems. All right, so 2 solutions for this problem right there. All right, next one was determine the general solution for the trig equation here. So again, we're just working our way through these equations. I'm going to kind of flip the 10 over to the other side of the equation, but it doesn't matter which side it's on algebraically. Maybe I'll just leave it as is. So 10 is equal to 6 sine pi over 4x plus 8. And then minus 8 divided by 6 gives me sine pi over 4x is equal to 10 divided by, or 10 minus 8 is 2 divided by 6 is 1 over 3. Okay. And then I arc sine both sides, so sine, let me just write it out here. So arc sine 1 over 3. Now 1 over 3 is not a special point on our unit circle. And that's going to equal pi over 4x. So I'm going to use my calculator. Now my calculator has to be in degree mode to work that, but otherwise I should just be able to put sine 1 divided by 3, and I'm going to get my values here. Okay, the first one I get is 0.34 radians is equal to pi over 4x. And the other one I get is, because sine here, it would be 180 minus 0.34 here. Okay, so pi sine, yeah, it'd be pi minus, oh, where am I? Second function, quit. Oh, there it is. Okay. So it'd be second function pi minus my value here, and that would give me 2.8 radian is equal to pi over 4x. Okay. Again, if you look at the unit circle, all right, sine is equal to 1 over 3 exists in quadrant 1 and 2. Okay, and they have the same reference angle wherever that reference angle is. It has the same reference angle on both sides. And so for the first one, it's just the number that you get in your calculator. For the second one, it's 180 degrees minus that first angle, either in radian or degree mode. Okay, so I have these 2 solutions algebraically. Last step, all I have to do is divide both sides by 1 over 4, or pi over 4, pardon me. And I get x here is equal to this one divided by pi over 4, which is 0.43, and the other one, this number, divided by bracket pi over 4, gives me the other value for x, which is 3.57 radian. Okay, so I have those 2 solutions. here I could ask myself, what is the period and all that, but I don't really need to do that in this situation. I can figure out that, yes, my period, but I don't have a domain that I have to fit these solutions in. So these are two values of x, but I need the general function. Okay, so these are two starting points, 0.43 radian and 3.57 radian. Okay, and here I'm going to add the period to each of these values to find every additional solution for an infinite domain. Okay, but for that I do need the period. So here my b value is pi over 4, and I know that my period equation is 2 pi divided by b, which in this situation is 2 pi divided by pi over 4, and that's an equation I actually saw earlier. I know that that's equal to 8. So again, here I know that both general equations that we've written have been plus 8. Okay, that's just a coincidence. Your period is not always going to be 8, so just know that. And then n, of course, needs to be integers. You can't be any numbers with decimals, but it could be positive and negative numbers there. Okay, so this would be your general solutions. All right. All right, now our last question here is looking at taking a word problem that is communicating some kind of oscillating or cycling phenomena in the real world and turning it into a trig function and then solving it from there to give us the solution that the question is asking for. So the question is, a mass is attached to the end of a long spring and is bouncing up and down. As it bounces, its distance from the floor varies sinusoidally with time. When the mass is released, it takes 0.4 seconds to reach a high point of 70 centimeters above the floor, and it takes 2.1 seconds for the mass to reach the first low point of 30 centimeters above the floor. And so we have two tasks here. Determine the equation for the distance from the floor as a function of time. And the second one is when does the mass first reach a height of 54 centimeters above the floor? So we're coming up with an equation that's just a kind of a function of time in function form, and then an equation that's equal to something where we can actually solve for a value of x or t, or in this case, or degree. All right, so in this situation, I want you guys to pause it, give it a try, see if you can find the amplitudes. Remember the A, B, C, and D variables. If you guys need a refresher for those, y is equal to A sine B bracket x minus C plus D, right? See if you can identify these variables in your question so that you can fill in your function, your trig function, okay? You could do sine or cos. When I answer it, I'm going to use sine, so you can maybe aim for that so you can double check your work. But maybe try to do both if you're comfortable with one. Try to answer both a cos answer and a sine answer, okay? But I'm going to be doing sine when I eventually answer this, okay? So go ahead and pause the video, give it a shot, and we'll come back together, go over it together. All right, hopefully that went well. A different kind of problem that we haven't seen before. So let's get started. First thing, I'm just going to work through my variables, right? I know this up here. A is my amplitude. B is going to help me find my period. C is the phase shift. And D is that vertical displacement. Okay, so first of all, amplitude. Let's start with that. Amplitude, I know, is max minus min divided by 2. So in this case, the maximum is 70, the minimum is 30, and I'm going to divide that by 2. So 70 minus 30 divided by 2 is equal to 20. So I have an amplitude of 20 meters or centimeters in all practicality here. Also, just to kind of visualize this, what's happening, so you have a kind of a steady platform here with a spring and a mass attached to it, okay? Mass. And this spring is just going up and down and up and down in an oscillating pattern. Okay? So that's my A value. Okay? I can solve for my D value because I know that when it comes to my vertical components, I know that the middle between the maximum and the minimum is my D value, okay? And so here, what you can do as well is you can take the minimum plus your amplitude, or the maximum minus your amplitude. That will give you your midline of your wave, which is your D value. So in this situation for D, I can take my minimum plus my amplitude. Okay, so in this situation is going to be the 30 plus 20. So I get a D value of 50. Okay, so it's coming along, right? I have the A value. I have the D value. Now I need my B value and my C value. Okay, the next one we're going to work on is that B value, and then we'll finish with the C value. We need to determine the B value first. So for my B value, so that's my A value here, my D value here. For my B value, one important equation here again always is this equation of period is equal to, now I have to choose whether I'm going to do this in radian or degrees. Okay, there's nothing in this question that is forcing me one way or the other. I'm going to do radian because I think my calculator is still in radian from last time, so I'm just going to use radian. So in this situation is pi over 2 over b. Okay, now I have to see if I can figure out the period of one full cycle up and down and then back up, crest to crest, trough to trough, whatever measurement for period you want to use. But I'm going to see if I can figure it out based on the information they give me. So first they say that the mass is released. It takes 0.4 seconds. Whoops, I need to highlight. It takes 0.4 seconds to reach the high point. And it takes 2.1 second to reach the low point. Okay? So to go from highest point to lowest point is half of a cycle. So if I can figure out how much time it takes for half a cycle, I can figure out the period for a full cycle. Okay, so a half a cycle, if I find the difference between those two times, 2.1 minus 0.4, a half a cycle takes 1.7 seconds. So if that's the case, then a full cycle would take, or a full period would take 3.4 seconds. Okay, so that's the period, 3.4 seconds. So this is equal to 3.4 is equal to 2 pi over b. Now I can solve for my b value. All right, so rearranging this equation, I end up with 2 pi over 3.4 is equal to b, which is equal to, I can reduce it here since I already have a decimal in the denominator, to pi over 1.7. Okay, so I'll use that as my b value. Be hard to get rid of the decimals here, then multiplying both by 10, I guess 20 pi over 34. But this is precise enough, 1.7, given the sig figs in the question. So now I have to figure out, okay, so what is the phase shift here? Okay. So it might be helpful to kind of sketch this out. So I have, I'm going to draw my midline. Okay, that's my midline, and that's above the x-axis, right? And it tells me at 0.4 is when it's released. Or sorry, it takes 0.4 seconds to get to the maximum, and another time to get to a minimum, and another time to get back to the maximum. Okay, so it's going to look like something like that. Okay, now I know that for a sine function, which is what I've chosen to do, my sine function graph should be starting at the y-intercept and the midline, okay? Because I know that should look like this, okay? So this graph has been moved to the left. There's a phase shift that's moved this graph to the left, but I got to figure out by how much, okay? One helpful kind of piece of advice here is to figure out how much time each stage of the wave, so the first increase, and then from the maximum to the maximum from the midline, and then from the maximum back to the midline, and then to the midline to the trough, and then from the trough back to the midline, right? So what is each quarter period? How much time is each quarter period? So I can determine each quarter period, each of these time segments, even though they're not drawn to scale, by taking my period and dividing it by 4, right? So each of these is 0.85 seconds, 0.85 seconds, 0.85 seconds, and 0.85 seconds, right? So from the time, if it was a regular sine function without a phase shift, from the time it goes from the midline to the first crest, would have taken 0.85 seconds, then drop back to the midline, would have taken another 0.85 seconds, then to the trough, another 0.85 seconds, and then back to the midline, another 0.85 seconds, okay? All right, but this is the actual line we're dealing with, okay? It's been moved. So I know that from the beginning, this takes 0.4 seconds, but without a phase shift, it should have taken 0.85 seconds, okay? So from there, I can, if I subtract, I need to find the difference here between 0.85 and 0.4. So the difference mathematically is 0.85 minus 0.4, which gives me 0.45 seconds. And that's my phase shift. And it's a phase shift in the negative direction. So I have a negative C value. Okay, that's probably the trickiest part out of coming up with these equations, is that phase shift. Okay, so don't be too hard on yourself if you didn't figure that out right away. You have to maybe rewatch it. We'll try to go through an example in our next class together as well. Try to clarify that. So now I just put this all together into my kind of template here that I mentioned. So y is equal to my amplitude is 20 sine, and then my b value was pi over 1.7 bracket x. Now it's x minus c, and because it's x minus a negative, this would actually turn into plus 0.45 close bracket, plus my d value is 50. Okay, so that is the equation we're looking at when all the pieces are together. Okay, yeah. All right, so now that we have our equation, we can use it to solve for specific examples. So, for example, the specific example they're talking about here is, when does this wave reach a height of 54 centimeters above the floor? At which times does that happen? So here they're giving me a height value of 54, so that's my y value. Okay, y is equal to 50, or height as a function of time, 54 centimeters. So I'm going to make my equation equal to 54 centimeters. So I have 20 sine bracket pi over 1.7 x plus 0.45 plus 50 is equal to 54. All right, and then I start solving algebraically. Minus 50 divided by 20 divided by 20. Okay, to cancel those out, I'm going to end up with sine pi over 1.7 x plus 0.45. And that's equal to 54 minus 50 is 4. And 4 divided by 20 is a fraction of 1 over 5, simplified. Then I'm going to use arcsine. So I'm going to left with pi over 1.7 x plus 0.45 is equal to arcsine 1 over 5. And that's not a specific point on our given on our unit circle. So we're going to use our calculator for this. My calculator, is in radian mode already, so I'm good to go. And so I'm going to get two values here again. Remember the two locations on your unit circle where sine is positive is in quadrant 1 and quadrant 2. So when I put arcsine 1 divided by 5, I get one solution, which is 0.20 is equal to pi over 1.7 x plus 0.45. And then the other solution, whoa, I didn't give myself a lot of space here for this question. The other solution would be pi minus this, right? Because it has the same reference angle, but in quadrant 2. So pi minus this answer gives me 2.94. So the other one is pi over 1.7 x plus 0.45 is equal to 2.94. All right, let's wrap this up. You can smell the end here, I'm sure. Divided by pi over 1.7 divided by pi over 1.7. Sorry. 1.7. That's nice and clear. So 20 divided by pi divided by 1.7 is x plus 0.45 is equal to 0.1. I'll say 1. Okay, then minus 0.45 minus 0.45, and I get x is equal to negative 0.34. Okay, which negative time doesn't exist in this question, or isn't outside of the domain, the logical domain of the question. So that would not be the solution that I would want to take. And so, let's solve for this one. Divided by pi over 1.7, that's going to leave me with x plus 0.45 is equal to this one divided by pi over 1.7 gives me 1.59 minus 0.45 minus 0.45. And x is equal to 1.14. And this units are seconds here. Okay, so that seems to be my answer. I can confirm using my graphing calculator that would be the first solution here, especially given that my period is 3.4. There would be no other solution coming before that. Okay, but I can confirm it by graphing, always by graphing 20 sine bracket, there's already a bracket divided by 1.7 bracket x plus 0.45 bracket plus 50, and here 54 I graph. Let's see if I can find some lines. All right, so my domain, or my one cycle, is 3.4, right? It looks like this. And the first time it's going to cross that height, which is what the question is asking for, is 1.14 seconds. All right. So hopefully these notes were helpful. Your homework assignment is here, and the due date will be included in the team's assignment description if you're in my class. Otherwise, I hope this video was helpful for you in general to better understand the concept. And we will see you next time.